right. I'm just going to pick on some people, okay? I'm going to call on Jack. Jack, what do we do here?
On number one.
On number one.
Change the 8 to with the fraction.
To the, what fraction would it be?
1/2.
8 to the 1/2. Okay. He's taking care of the inside. Gavin, will you take care of the outside?
Yeah, and then the 8 to the 1/2 then gives that to the power of 1/4.
Very good. Okay. So we've taken care of the radical on the inside. It's represented with the power of 1/2. Taking care of the radical on the outside. It's written with the power of 1/4. Did I do something wrong?
Is your screen red?
Oh, it is. It's frozen. Dang it. Forget that all the time. Okay. How's that? Nice. Okay, power to a power, we multiply those. So this is going to be 8 to the 1/8. Let's see. Then I can write that as the 8th root of 8. Is there anything else I can do? We could think of changing that into 2 to the 3rd, but is that going to help very much? No, we probably end up just changing into that. They don't have any common factors, the 8 and the 3, so that's not going to help us a whole lot. We talked about this one yesterday. Okay, listen very carefully. Radicals deal with multiplication. Okay, they play really well with multiplication and division. They do not play well with addition and subtraction. So you can't break this up. There's no addition or subtraction property of radicals. Again, this long bar right here, whenever you see a long horizontal bar in math, it's a grouping symbol. These are grouped together. You got to figure that out first. So this isn't the square root of 16 plus the square root of 9. Might be kind of cool. Doesn't work that way. This is the square root of 25. So the answer is 5. Hoping we're getting good at this. Radical 3 times radical 3. Luke?
3.
How come?
Because there's 2 pairs of 3.
Yeah, pair of 3s. There we go. Minus 2 radical 3. And then we've run into this pattern before, so this is going to be a plus 2 radical 3 and then minus a 4. I should write that as a 3. Those middle ones are exact opposites from each other, so they cancel each other out. They don't combine to be anything other than 0. So then we end up with a 3 minus a 4, so we end up with -1. Raise your hand if you got that on your own. Excellent. Okay, and then this one is that big ugly mess where we've got a bunch of radicals floating around. Multiply here and here. 2 radical. I'm going to think, hey, there's a 5 and a 3. Can I factor anything? Can I get any more factors? I can't. I need pairs, so this is going to be a 15. I'm going to multiply here. I'm going to think the same thing. Do I have any pairs or anything? I don't, so this is going to be minus radical 15. I'm going to multiply here, so this is going to be a -2 radical. I only have a 2 and a 3, so that's going to be a 6. And then I multiply here, and I get a, let's see, that's going to be a positive. I've only got a factor of 2 and a 3. I need pairs. I don't have any pairs, so I end up with this. So those are like terms. I end up with a radical 15. And those are like terms. I end up with a negative radical 6. Neither of which can be simplified. So are we stuck with this? We are. Okay, does anybody notice anything about this particular problem in the way it's written? I haven't done this one before, but I just noticed something. Anybody notice this last factor right here? Do you notice anything about that? 2 radical 3 minus radical 3, what would that be? That would be radical 3. So we could take this and we could change this problem into radical 5 minus radical 2 times radical 3. And if you distribute that through, doesn't that produce radical 15 minus radical 6? It does, okay? So lesson about simplification. I just got done teaching a couple classes where we're reviewing equation solving skills. The first thing we want to do is we want to simplify before we solve because that makes things easier, okay? Just notice that one. Okay, so here's what we've got down below here. This is an absolutely enormous set of numbers, some of which you're familiar with, some of which you're not. And I'm going to tell you, part of this falls into the category we talked about yesterday. Nice to know, absolutely critical, probably not, but we are going to introduce some important ideas here. And if you go on in math, you're definitely going to see this stuff right here. Luke ought to be interested in this because I'm going to use the example he gave a couple weeks ago. Okay, Okay, and then the other thing is this closure idea, talking about closure and operations of sets of numbers and things like that. If you go on and study any higher math, that idea comes up a whole bunch. So forgive my penmanship to start off with. Okay, we're going to start right in the middle of this gigantic set of numbers, the natural numbers. So those are the counting numbers. You learn to count with 1, 2, 3, 4, and so forth. And we usually use script letters for this. So again, I'm really horrible at this. So it's kind of like that. Okay, kind of a cool looking N. Sometimes we'll do them like maybe a double line right here, something like that. I don't know, just make it look a little bit different. Okay, then whole numbers, what we do is we add 0 to that. So in elementary school, or when a little kid learns numbers, they don't start with 0 because 0 is actually a pretty advanced idea. So we add 0 to that, and we end up with the whole numbers. So we're going to use a W for that. Just pretend like mine looks pretty. Okay, make yours look however you want. Okay. Then we add the idea that we can have negatives. Positive numbers don't represent everything. 0 doesn't represent everything. We've got to have the opposites of those. For integers, we use a Z. It's from the German word, I think it's zählen, means to count, has something to do with accounting or something like that. So we're going to do a Z like this, kind of like a double wall on that guy right there. And I do not have these memorized, so I always look at them. Okay, next one is rational numbers. Remember, the root word there is rational. So these are numbers that can be written as a fraction. So we kind of use a double wall right there. So those are rational numbers. Oh, take that back. Take that back. See, I told you I didn't know these. Okay, it's a Q. I should have looked at my own notes. Okay, the Q used for rational numbers, I just put a little Jeopardy hint over here. Something like that. Okay, stands for quotient. Okay, so if we're setting up a ratio, that's going to be a quotient. Okay, now the real numbers, those ones are R's. And you've talked about real numbers before. Okay, and just kind of another point of interest, you learned about prime notation. Prime notation that you've seen was used to represent a new figure after a transformation or something like that. What it means here is it means the complement of a set. So when we're talking about sets, something is either in the set or it's not in the set. And if it's not in the set, then we say it's part of its complement. So for irrational numbers, the one down here, we're going to do a Q, so kind of a Q like that. And then we're going to put a little prime notation next to that, something like that. Let's see, complex numbers. Luckily, that one's kind of what you'd think. And then this is kind of the interesting one. Okay, so here's the example we're going to do. And for this, I'm going to kind of blow this up just a little bit. The next example I want you to add is the square root of negative 36. So we talked about this, I think, last week. So the problem with taking the square root of negative 36 is if you square something, if you multiply it by itself, if it's negative, two negatives are going to make a positive. If it's positive, two positives are going to make a positive when we multiply them together. So there's no way to make a negative 36. But that's still asking for pairs of factors. Okay, and Luke, do you remember this one?
Yeah.
What did you say we do with 36?
I said we turned it into 6 and then square root negative 1.
Okay, so we're going to write this as square root of 6 times negative 1. So we're going to take the 6 on the outside, and then we're going to leave a negative 1 on the inside. Okay, and that's where this comes in right here. So the I is first of all, imaginary is a horrible name for these because they do exist. If anybody has a mom, dad, somebody like that who's an electrical engineer, or they do hydrodynamics or aerodynamics or anything like that, imaginary numbers are actually real. They get used quite a bit when they're solving stuff in those fields. So they do exist. They just used an I for this, and this is what they said. They said, hey, if we're left with a square root of negative 1, like if we can take out pairs of factors, great, let's do it. Let's pull the 6 out. If the only thing left underneath the radical is a negative 1, let's just call that I. So the square root of 36 is 6i. We'll do one that's slightly more complicated. square root of negative 7. So we apply the exact same idea to this and say, look, I can't deal with the negative, but I can at least deal with the positive part of that. So that's going to be the square root of 7 times the square root of negative 1. So separated into pieces that we know how to deal with. We know about the square root of 7. So this would be 7, square root of 7i. And we normally write the I out front. So we'd normally write I square root of 7. Okay? So that's how we deal with the square root of negative 7. And don't worry, we're going to talk about this more because we'll run into these a whole bunch later this year. We're just talking about number systems for the time being. So these are all the number systems probably that you're ever going to deal with. I haven't dealt with a whole bunch of other number systems other than these, so this should kind of take care of it. So I'm going to blow this up to the point where we can see this right there. And then at the bottom of the screen, it's just 3 problems. And you've got some problems like this on your assignment. They go really quickly. It says circle all of the number systems to which each number belongs. Now, I think I switched the order on this because I wanted that complex one at the end. Complex numbers cover any number that you could possibly run into. Okay, so to make sure we're clear on this, you don't need to write anything down. Here's what I want you to look at. These are all the numbers that you've ever used. Okay, the real numbers, that's the only thing that you've ever used. Okay, we just really quickly introduced the idea of what an imaginary number is. So it's either real or it's an imaginary. And if we take those numbers and we put them all together, we get a group of numbers called the complex numbers. Now, even with all the math that I know, having a bachelor's and a master's degree in math, I really don't think I've run into any numbers that don't fit into that gigantic group. There are numbers that don't fit into that group, okay? But this is what we're going to study. And for all intents and purposes, that's all you're ever going to need. So the way we get a complex number is anything in here is a complex number. That's the big group that it belongs to. Okay? It's the most general group. Anything in here that has an I or a square root of a negative or something like that, it's over here. But when you put those and add them together, so for example, the number up above, it says 4 plus 3i. We're taking the real number 4 right here. We're adding the imaginary number 3i. That number together, we call that a complex number. The next example, a 2 minus an I. We've got a real part of 2, an imaginary part of negative 1i, and that's a complex number. Don't sweat that too much. We're going to get to the point where we'll see these a whole bunch, and then we'll be in good shape. So what I want you to do is take a look at the numbers down at the bottom. Square root of 49. Does that make us nervous at all? Hope not. That's a 7. So what is it? Is it a natural number? Is it one of those counting numbers that you learned to start off with? Yep. Is it a whole number? Yep. Is it an integer? Also an integer. Okay. Mason, will you pull that door shut? What about a rational number? I see a couple shaking heads, yes. Dane, what makes this a rational number? Not because it's written as a fraction, but the question here is, can it be written as a fraction? And the answer to that is yes, 7 over 1, so it's also a rational number. Now, if you think about the way these groups are set up, it's rational or it's irrational. It can't be both, all right? So if we say something is rational, we can automatically cross the next one off and we can say, you know what? It's not irrational. Is it a real number? Yep. Is it imaginary? No, because it doesn't have the I. Is it complex? Yeah. So guess what? Could you circle these right now without even looking at the numbers? Could you say that every one that we're going to run across is complex? Yep, we could. Now let's come up and let's take a look at this. Definitely going to be complex for each one of these. Take a look at radical 3. Does that make you a little nervous? Grab your calculator, type it in. This has an asterisk because what you got on your calculator is a decimal. Now, just because it's a decimal doesn't mean that it's rational or irrational. We need to be a little more sophisticated than that. That's where this asterisk is over here. Okay, so how can you tell if a decimal number is a rational number? Yep.
It'll either stop or it will repeat.
Very good. So we're going to say this. It will either terminate meaning it's going to stop, or it will repeat. So we've already seen some of these. The number 7, 7.0, it stops. 0.5 stops. 0.3 repeated is the same as what fraction? 1/3. Okay, that one's 1/2. That one's 7/1. So it's either going to terminate like this, 0.125. Anybody know what 0.125 is? Mason. It is 1/8. Okay, and if I did this, 0.125, and I put a bar over the 125, now I'll be honest with you, I don't know what 0.125 with a bar over it. 0.125, 0.125, 0.125. But what I do know is if it repeats, there's got to be a way to turn that into a rational number, turn it into a fraction. And these calculators are sophisticated enough. If you fill your screen up with 125, 125, 125, 125, 125, and then tell it to change it to a fraction, it will say, thank you very much, 125 over 999. Okay? And there's a pattern to that. So let's come back to this. This is a big, long, ugly decimal. Is it a natural number? No. Is it a whole number? No. These are really nice numbers. Natural numbers, whole numbers, integers. Is it a rational number? It is not. If it's not rational, that means it's irrational. Now, can somebody tell us, how do we know radical 3 is not rational? Looking at your calculator, how do you know it's not rational? Brittany? Very good. It doesn't stop and it doesn't have a repeating pattern. Excellent. So pi is another example of an irrational number. Doesn't have a repeating pattern, never stops. Okay, this one right here, we dealt with this up above. Oh, forgot. Real? Yes. Imaginary? No, doesn't have an I. Okay, what was this one up above? Square root 7, square root -1. So we'd say I radical 7. Natural? If you were counting with that number when you were 3 years old, that would have been amazing. Whole? No way. Integer? No way. Rational? Nope. Irrational? Nope. Because it fits in that other category once it's got that I on there. So it's not real, imaginary. Okay, we good there? Okay, flip the page over. Okay, you might remember that about a year ago when you were in Secondary 1 Honors, we were going through and we were solving equations and we were doing justifying the steps with all the properties, commutative property, associative property, additive property of equality, different things like that. Okay, today we're going to talk about a different type of property. It's called the closure property. So write the word closure right here. Okay, now, reading a math statement or a math textbook or a set of notes is a skill that we can learn to develop. So we're going to read this really slow. There used to be a guy on the radio who would do a thing that the news always makes sense if you read it real slow. So he'd read the news real slow and let you think about it. A set is closed under an operation. Ooh, operations. Add, subtract, multiply, and divide. If and only if, that's a weird way to say that, if the operation on any two elements in the set produces another element in the same set. So operation, if and only if. So we have to have two numbers. We're going to do an operation. We're going to add the numbers. We're going to subtract the numbers. We're going to multiply them. We're going to divide them. And it says it has to produce another element. We're going to say number of that same set. If the operation produces even one element outside the set is not closed. And guess what another way to say not closed is? Open. So here's what we're going to do. We're going to check a bunch of numbers and we're going to say, hey, if I add these, if I subtract them, if I divide them, if I multiply them, whatever I happen to do, does it produce another number in that particular number set? So there's a little bit of logic going on here. And if it doesn't, if there's even one time, if we run into one example that says, nope, it actually doesn't work that way, okay, then it's not going to be closed, it's going to be open. Okay, so all that's needed is one, would you underline the word counterexample? All we need is one counterexample to prove that closure fails, or in other words, it's not closed, but it's going to be open. So here's what a counterexample is, because you're going to hear this repeatedly in the future. So what's a counterexample? An example that contradicts a statement. In other words, it proves the statement is false. So the instructions or the questions that you could be asked about stuff like this, okay? Tons of different ways it could ask. This is kind of a typical way of asking questions like this. We're going to focus on one set, the integers. So the script letter that we use for that is Z. So the question here is it open or closed? And then we've got to give an example or a counterexample. So if the set's closed, okay, then we give an example of why it's closed. If the set is open, then we give a counterexample that says, hey, this doesn't work. Okay? So we're using integers, positive and negative whole numbers, including 0, the nicest set of numbers you could possibly ask for. So when we say, is it closed or open under addition, what we mean is, if you add two integers together, do you get another integer? So let me say that again. If you add two integers together, do you always get another integer? I see some shaking heads. The answer to that is yes. So this is closed. So somebody give me an example. I can add two together and it'll produce another one in the set. Keely? 2 plus 2 is, whoops. Hop to the answer. 2 plus 2 is 4. I'm going to do 2 plus negative 5. Because it said you had to add them. That's a weird way to write it. What do we end up with? Negative 3. Do you start with integers in the operation, and do you end with an integer after you do the operation? So there's a couple of examples, okay? So this is an example, okay? Subtraction. If you subtract two integers, do you always end up with another integer? Answer to that is yes, so this is going to be closed. So an example would be something like this. Negative 2 minus negative 7. That'd be negative 2 plus 7, so that's going to be a 5. I started with integers, I did an operation with it, and I still have an integer. If you multiply two integers, do you always get another integer? Yes, you do, so that's also closed. Pick any example you want. I'm going to do negative 6 times 7, and I end up with negative 42. These are all examples. Okay? All of these are examples. Now, if you divide two integers, do you always get an integer? Answer to that is no, so that means this is open. So what we're going to do now is, I'm actually going to change colors just to make this more clear. I'm going to write open, and I'm going to spell it right, and then I'm going to come up with a counterexample. So my counterexample is going to be this. If I take negative 2 and divide it by 10, I end up with negative 1/5. Not an integer. There's my counterexample. Okay, now, if I were to flip that over, 10 divided by negative 2, I get a negative 5, right? There, I just divided two integers and I got an integer, so it should be closed. Is that true? Okay, listen very carefully. Providing one or even a million examples doesn't prove that something's true. You can provide as many examples as you want. That is not a proof that it's true. But if you provide one counterexample, that proves it's false. So that's the power of a counterexample. It only takes one example to show that a statement is false. All we need is that one right there. Make up any other one you want, and then you're just fine. So slide down here. We're going to take a look at the last of this, and then I'll hand out the assignment. It says determine whether the statement is true or false. If it's false, then give a counterexample. The sum of two irrational numbers, think radicals for the most part, radicals of ugly numbers, is always irrational. So we're going to add two ugly radicals together, and we're going to get another ugly radical or something. Does that always happen? True, false? Si?
False.
You think it's false? He's right, it is false. Can somebody give us a counterexample where you take two ugly numbers that are in radical form and you put them together and you get something that's not in radical form? Brittany? Okay, radical 4 plus radical 5. This would be 2 plus. This would be, if you check, this is 2 point blah, blah, blah. You're going to end up with 4 point blah, 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 no repeating pattern, okay? So that's not going to be a good counterexample because that's still irrational, okay? Yeah.
It's radical 4 plus radical 4.
Okay, radical 4 plus radical 4 ends up being, so we've got a 2 plus a 2. Okay, so the problem is, what are we starting off with? We've made kind of the same. Rational and rational make irrational. This one's rational plus an irrational. Okay, might want to keep that in mind. These are common things that we do. Yeah.
Radical 3 plus radical 3.
Radical 3 plus radical 3. That's irrational. Add it to an irrational, you get another irrational. But this statement is actually false, so we want to come up with a counterexample. We can what?
I think I've got one actually.
Okay. All we have to do is change one thing on this last example, and we've got a counterexample. This is irrational. Add it to this irrational, you're going to get another irrational. But anybody know what to do? Luke, you want to take a stab at it?
Make it negative.
Yeah, make that one negative. That's irrational, and that's irrational. And when you put them together, what do you end up with? You end up with 0. Okay, so there's our counterexample. We got an irrational plus an irrational, ended up being rational. The product of a rational number and an irrational number is always irrational. So if you take a rational number and multiply it by an irrational number, it's always going to be irrational. Give you a hint, it would be pretty boring if it was true. And I'll give you one other hint. 0 is a pretty unique number. It's got a lot of very interesting properties. Mason?
Well, I was going to say, multiply like root 3 times 0.
Yeah, sure. 0 is a rational number. We're going to multiply it by an irrational number 3, and we end up with 0. So here's a case where we start with something rational, times it by something that's irrational, and we still get something that's rational. Okay? All right, everybody good? Okay. This is one of those that takes more time to explain than to actually do. You'll notice the back side of the paper I'm handing out is blank. That means the front side is the whole assignment. Oh, wow. I didn't even make the worksheet, but I'll take the credit for it. Okay.
And then you're going to remove like multiple
There's 19 problems on here. It follows along with what we were doing.